So this problem is following up directly on the heels of yesterday's work. Now remember yesterday we learned something called the change of base formula. And so for doing this work, we got to use the change of base formula. That's the one where we do log divided by log. Specifically, the base, remember, goes on the bottom. Now when I say the base goes on the bottom, remember the base is the small number here. Notice it's written shorter than the original, it's written lower. And so that's the number that goes here. It's also written lower in the fraction. Now it's just a matter of doing that calculation. Now when you actually did this calculation, you do log of 300, and it gives you some weird looking decimal, right? 2 point something. And then you say divide by log of 10, and that gives you actually a pretty looking number. What was log of 10? 1. When you typed that into your calculator and you did log of 10, it ended up showing a 1. And then you pressed equal to do the division, and so it gave us 2.48. Once we rounded it to the nearest hundredth, of course. But now, notice then, this gave us 1, right? Dividing by 1 always gives us the same thing. So I technically didn't even have to type in the log 10. But don't we have to use change of base formula? Yes, but the change of base formula is used to change the base to something we can work with. This particular example that I gave you actually was to help you see what the base is. Because I could have actually written this original problem shorter, and it would have meant the same thing. I could have just given it as log of 300. That's the same thing. When we do not write the base in, it's assumed to be a 10. Because if you divide by log 10, you just divide by 1. It means the same thing. And so it's probably worth reminding you of that for future. So make a quick note of this in where you've been writing down your other logarithm rules, that log is the same thing as log base 10. Today's focus is going to be all about algebraic work. How do we solve equations now using the work that we learned yesterday and actually the day before? So we're putting those pieces together to solve equations. Now one of the things we talked about yesterday is that log solves for the exponent. You solve exponentials by writing them as logarithms. This is going to be the big idea. So step 1 in solving this equation, which if you haven't written it down yet, write it down. Step 1 is to rewrite that equation in logarithmic form. So I want to write that as a logarithm. Whenever you write it as a logarithm, of course, the very first thing we write down is log. What is the base of my logarithm going to be here? It is 8, yes, because that's whatever is to the power of something else. So that's always what goes there. Then what number goes here? Is it the x or the 80? 80. It is the 80. Now, if you don't remember that, if you have a tough time remembering that one, you can always remember log equals the exponent, and then process of elimination would tell you it's the 80 as well. And so we now know that x equals log base 8 of 80. Oh, a little side note here. I wrote it as x equals. If you wrote it instead as just log base 8 of 80 equals x, yes, it means the same thing. It doesn't matter which side you put the x on. I just put it on the left because I think it looks a little cleaner and some personal preference.
Would have mattered during the test. No.
All right, so now I know what x equals. I know that x equals log base 8 of 80. It's just that now I have to actually calculate that value. Now we go back to where we started class, right? We got to use change of base formula. Notice I cannot just type in log of 80 here because it's an 8, not a 10. So we have to use change of base formula. So we're going to do log of 80 divided by log of 8. Remember, the base goes on the bottom there. Go ahead and do that calculation, please. And so when we do that calculation, yeah, we end up with about 2.11 if I round it to the hundredth at least. Now, since we can solve that last one, then we can start adding some layers to it using the algebraic skills that you already have. Because, of course, we've been building up your algebraic skills all year long. So we're going to jump now into this one. Write it down first, of course. And when you're solving exponential equations, that is something where we're solving for the exponent, you always want to get the exponential part by itself first. So I'm trying to get it to be 5x equals right now. So that means getting rid of the 4. What do I do to both sides to get rid of the 4? We divide, yes, because we are undoing the multiplication that's currently there. So if I divide both sides by 4, I get 5 to the power of x equals 25. Now, we got 5 to the power of x equals 25. Notice we're trying to solve for the exponent. So, we're probably thinking we got to turn it into a logarithm then, so let's go ahead and do that. If I write that as a logarithm, we get x equals log base 5 of 25, which I could calculate by using change of base formula. It'd be log 25 divided by log 5, but some of you might have already noticed, in this particular case, you didn't even have to go through all of this, because 5 to the power of what equals 25? 2. So if you had seen that right from here, if you had said, oh, I know what it is. I know 5 squared is 25, so I know x equals 2. You could go straight from there to here. But notice it's only because it happened to be a whole number that we could know off the top of your head. If you don't know it off the top of your head, well, then you go ahead and go through the log forms and do those calculations, because they'll still give you the answer of 2. All right, so when working through this problem, again, the first thing we want to do is get the exponential by itself. So notice here, that's the 3 to the power of x. So you want to move that 9 over first. So we're going to go ahead and add 9 to both sides. And so when you add 9 to both sides, you have 3 to the power of x equals 90. What do we do to it next? Well, I'm solving for an exponent. One of the things I want kind of locked into your memory here as we go forward is any time you're solving for the exponent, you're going to turn it into a logarithm at some point. And since we have the exponential by itself, now is the time. So I'm going to go ahead and put it into log form. That's going to be x equals log base 3 of 90. Okay, now it's time to actually do that calculation. And so we do that calculation by doing log of 90 divided by log of 3. And then plug that in your calculator. And so when you do that calculation, you end up getting 4.0959 and so on. Now I don't care about that last 9, but I do see 0.95. Am I going to leave it as a 9? No. That means I have to round it up. But if I'm going to round that up, the 9 doesn't become like a 10 like that. That wouldn't be right. We carry that 1 up, and so it becomes 4.10. So with this one, we now have both steps that we were just working with individually now put together in one. Again, I'm trying to get the exponential part by itself first. So that means the 10 to the power of x I want by itself. That's going to be what allows me to then turn into logarithm. So I got to get rid of the 7, I got to get rid of the 26. When doing that, think about going backwards through the order of operations. So like, you know, PEMDAS, right? When doing an equation like this, when solving an equation, you're undoing it. So you're actually wanting to go backwards through it. So the very first thing I want to do is I'm actually going to want to move the 26 to the other side. So I'm going to subtract 26 at the start. Now, in case you're wondering, wait, I thought I could divide by 7. Technically you can, but if you do, you'd have to also divide the 26 by the 7 as well as the 54. They both give us ugly decimals. It's not as much fun. It's not as clean. It's a lot easier for you if you just subtract the 26 first. All right, now that we're here, you can move the 7 over. So now go ahead and divide both sides by 7, and then go from there. And so from here, we know that we're solving for the exponent, so I need to write it in logarithmic form. When we switch it into log form, we end up with x equals log base 10 of 4. Now we need to calculate that value. And what I'm expecting is that most of you actually probably did it this way. You probably did log of 4 divided by log of 10. However, we didn't have to, remember, Because remember, this is log base 10 of 4. Log base 10 is that one unique situation where I don't actually have to write the base in. That would be the same as just log 4. So you actually could just do log of 4 in your calculator and not even worry about the divide by log of 10 because it's 10. But either way you do it, you get the same answer of about 0.6. So we're now going to take what we've seen with all those and we're going to tackle this problem. Now this problem, it looks simpler, but you're going to notice there's going to be a little wrinkle that comes into it. Some we're going to have to know how to deal with accurately. So we're going to write down this problem and start working it through. The first thing we of course want to do is we do want to try to get the exponential by itself as normal. So I'm trying to get the 3 to the x by itself. So I got to get rid of the 7. So I'm going to divide both sides by 7. But all of a sudden something seems a little different here. We get an ugly number. We get a decimal here. It's no longer an integer value. So 121 divided by 7 gives me 17.2857, a whole bunch of decimals here. I don't really want to have to write out the whole decimal every time. Now when I get a decimal like this, I don't want to have to write out that whole thing every single time. I don't want to retype that in. So there's some little techniques that we can do when we do this work. The first thing is that when I write this sort of thing out, I actually on my paper, when I'm doing these math problems, I don't write out that whole decimal like that. I actually will call it like 17.28 ...
Not even 2.
This is what I'm writing down. What this is doing
Can't you just do
is it's showing that it gives me a decimal that starts as 17.28, but the ... is different from rounding it. It's saying that this decimal keeps on going on forever. Now why would I do that instead of writing 17.29? If I write 17.29, at least for me, when I look at my paper, I think it equals exactly 17.29. And so I might then just type that in my calculator. By typing those dots in, or writing the dots down rather, I don't actually type them into anything. I remember this is just the start of a decimal that goes on forever. And I'm just writing it down for my own benefit. Now you can do whichever one you want to. You can write down the rounded version if you want to here. But we're going to be talking about how we make sure our calculation comes out accurately. And you're just going to make sure you use the whole decimal in your calculator, as we'll talk about. So once I've gotten to this point in my calculation, you notice I want to solve for the exponent, so I turned into logarithmic. And so this is the way I would write that. I would actually write that as x equals log base 3 of 17.28 ... Yeah, and again, you can write it down as the rounded version here if you want to. But remember, that's only what you're writing. Remember on my calculator, I did 121 divided by 7. I haven't used my calculator for anything else yet. The next thing I do in this problem is I now need to use change of base formula. So I'm going to write that as the log of 17.28 over the log of 3.
Right.
And again, I'm just keeping those dots there showing that this is just the first few digits of the decimal. I now need to do the calculation. Remember how I said that this whole decimal is still showing on your calculator? Well, the very first thing we want to do is log of that. And so we're going to take advantage of the fact that your calculator is already showing it. We don't want to press clear and then retype it back in. Now, again, it depends on what type of calculator you are using. I'm going to start with the scientific calculator. So like if you're using one of mine here in class, what you would type into the calculator. Remember, this 17.28 is already showing on the screen. So the first thing you press is the log button, and then you press divide, and then you go 3, then you press log, and then you press the equal sign. And again, that's for a scientific calculator. Now, if you're not on a scientific calculator, you're on probably a graphing calculator. One of the cool things that graphing calculators have is they have an answer key. On almost every calculator, it's second negative, right next to the equal sign. So if you're using one of those, what you're going to type into your calculator with the 17.28 number still showing is you're going to type in log, So press the log button. And then you're going to go second, and then you press the negative button. Notice it's not the minus, it's the negative key right along the bottom. That has the yellow ANS written above it. And so as soon as you press it, what you're going to see on your screen is log ANS. That ANS actually represents the entire last decimal that it calculated. So it's plugging in that whole decimal for you. You don't have to retype it in. This is a win-win for us though, because it's fewer keystrokes and it's more accurate. It's a win-win. So use that. So once you plug that in, then it's the normal calculation like normal. Remember on the graphing calculator, you need to end your parentheses before you divide by log of 3. If you do that calculation correctly, you should get an answer of about 2.59. Make sure you can get that answer out on your calculator as well. This is going to be the last problem we do here together. Please take a moment, write down the problem, and then we'll start working it through and seeing how it goes. Once you have it set up or written down, go ahead and try setting up your equation as well so we can check that. Now, when you wrote this down, if you shorthanded it at all, let's make sure you got some of the critical information down. Always make sure to at least write down the numbers that were involved. At least. And it's a good idea also with that to make sure that you put down like what was the starting value, what was the ending value, some stuff along those lines. All right. So we're going to be writing our equation. This is the equation that's going up by a certain percent each year. So that tells me I'm going back to A of t equals the one that you should memorize, p times 1 plus r to the t. So we now need to start plugging into this. Okay, do we know what p is? Yes, we do. Question is, which number is it? Remember, p stands for principal. That means our starting value. What does this start as? 150. So it's going to be 150 parentheses 1 plus r. What is r here? Now, of course, we got to be careful, right? It's not 4, but it comes from it. We still have to turn that into a decimal. So yeah, 4 divided by 100 is 0.04. To the power of t, do I know what t is? No. So I know this much. A of t equals 150 times 1.04 to the t, but of course I haven't used one piece of information here, the 350. Where does that go in this? Well, I got two options. It's either A or it's t. A represents the final amount. T represents the number of years. Well, that looks like it's a dollar amount, not a time. So that's going to be the A value. But I now want to bring up something to you and make sure you're aware of this. Please do not write it like this. It is not 350 parentheses t. Because this would mean 350 times t. But that's not what this means, remember. That means A of t, not A times t, A of t. In other words, the value of A at t. So we don't include the t there. It's just 350 equals 150 times 1.04 to the t. All right, now based on the work we did earlier, you know what to do first here to solve it, right? What am I going to do first to my equation? And so again, we are trying to get that exponential part by itself. That means getting rid of the 150. So we divide both sides by 150, but notice, again, we end up with one of those big long decimals. So remember what we were just talking about with the last problem about how to keep track of the decimals? Leave that number showing on your calculator because it's probably going to be the next number you need. You're going to save yourself some grief by not pressing clear right away. Now, when I wrote this one down, instead of writing 2.3 dot dot dot, you'll notice I wrote slightly differently this time. I wrote 2.3 with the line over the 3. Because the 3 does just repeat forever, I could write it down exactly and save myself some writing at the same time. There's nothing wrong if you wrote it down as 2.3 dot dot dot, but I just think this is a little bit more succinct. All right, next step, we're solving for x. X is the exponent. What do I always use to solve for an exponent? It's logarithms every time. Whenever you see the unknown in the exponent, whether we call it t or call it x or whatever we call it, if you're solving for the exponent, you will have to write it in log form. And so when we turn this into log form, this is what it looks like. Now, at the moment, I know some of you are looking at it like, I feel unhappy now. There's too many decimals. But notice none of the decimals are in places where it's going to actually cause us any problems or anything like that. This is really just the same kind of stuff as we've been doing. Yeah, the number's a decimal, but it's still the exact same calculation that we're used to doing in order to be able to do something with it, right? So, now, calculate that value. And of course, write out the work on your paper that you're going to use to do that. All right, and so in order to do this calculation, we're having to use change of base formula, right? The very first thing we're going to do is log of 2.3 repeating. And since that 2.3 repeating is what's currently showing on your calculator, all you got to do is press the log button for it. You don't have to retype it in. This is saving you energy, and it's more accurate. Come on, win-win, right? Then we divide it by the log of 1.04. When you do that, yes, your correct answer here should be about 21.60. So with the correct rounding, that's what you should get. But I want to point out, what if we didn't use the whole decimal? What would happen? Well, you notice this 21.6 looks a lot like 22. If we're talking how many years is it going to take, thinking of it as 22 years is fairly reasonable. But what if we hadn't used 2.3 repeating? If we had just used 2.3 instead, you would have gotten 21.24, which looks a lot more like 21 years than it does 22 years. We don't want to be off by a whole year here. And so that's why we actually need to use the entire decimal. Otherwise, those little tiny amounts of rounding error up here become big differences later. So we have to use the whole decimal or it will throw off everything you do.